Okay, this is the last video on explaining your second project, the computation of the Feigenbaum delta. To give you an idea of how accurate this constant has been computed, this is what I pulled from the web. The delta is 4.669, and then we have all these digits. So obviously, in double precision, this is impossible, right? Because we're limited to the number of digits that we can hold in a number in the computer. So it's possible to use unlimited precision in MATLAB. And as a challenge, I ask you to do that, but this is not really part of the course. I had a lot of fun doing that at one time. So in this course, then, I'm asking you to compute the Feigenbaum delta to as accurate as you can in double precision. So in the first lecture, I give you some theory that the Feigenbaum delta is a constant which measures the period doubling approach to chaotic solutions in a nonlinear system. It shows up in a lot of different systems, but the easiest system to look at it in is the logistic map. In the part B, I detailed to you an algorithm for computing the Feigenbaum delta that makes use of root finding, and in particular Newton's method, which is the fastest possible method for finding a root. Now in part C, let me just briefly discuss the computational engine of the code. Okay, the part of the code that will implement the algorithm. So we have three loops, three embedded loops. The outer loop is going to loop over the period that we're looking at, right? So we're starting with period 4, because we did the m values for period 1 and period 2. So the first one we need to do numerically is the m value for period 4. That's 2 to the 2. So we're starting with n equals 2. And in the outer loop, then, we're going to go from n equals 2 to n equals 3 to n equals 4, etc. So we can do that with a for loop, right? So this is essentially for n equals 2 to some maximum value, okay? So in each iteration of this loop, we're going to increment the value of n. What do we do at the beginning of this loop? We need to have an initial guess for the m sub n that we're looking for in this value of the loop, right? In this n value of the loop. We're looking for m sub n. The initial guess we get from the two previous values of m, and the guess for the Feigenbaum delta, which actually depends on the three previous values of m. Okay. Initially, we don't have enough m values. We only know 2. So we're going to just start with a delta 1, say, equal to 5. And after that first pass through the loop, then we'll be computing the next values of the estimates for the Feigenbaum delta. Okay, so that's loop 1. In loop 2, then, we're going to iterate Newton's method. You can iterate Newton's method a fixed number of times, or you can use a while loop and stop your iteration when you've converged to somewhere close to machine epsilon. Okay, delta is around 4, so it's 4 times machine epsilon, somewhere around there. Okay, so either do a for loop with a fixed number of iterations or a while loop here. To do Newton's method, we have to compute the value of x sub n n is 2 to the little n, x sub big N, and x prime sub big N. We need to iterate the logistic map. So we need to initialize the logistic map. So here we set the value of x to 1/2 and the value of x prime, say you can call it something like xp, equal to 0. Then in loop 3, we iterate the logistic map. So we have to iterate the logistic map 2 to the n times, capital N times. So this iteration of the logistic map then has the most, is done the most times, right? The inner loop always has the most times it's being computed. Here we're computing x and x prime. These two lines then will take up the most of the time of your code, okay? Because you're iterating the logistic map 2 to the n times every time you go through this loop. You know, if n equals 10, it's already 1024. You're probably going up to n equals 15 or so. Okay, so many, many times of iteration here. So loop 3 ends after you've finished iterating the logistic map a capital N times. Then we can apply the formula for Newton's method to get a slightly better estimate for m. So we apply Newton's method on mu, g of mu, to try to get a better estimate for m sub n. Then we end Newton's method after Newton's method converges. So we loop through loop 2 a handful of times. It doesn't take very long for Newton's method to converge, maybe 3 times, 3-4 times. So we have to go loop until it converges. Then loop 2 ends, and we've computed our value of m sub n. You need to save it somewhere. You can't let it go away. You can compute your Feigenbaum delta at that level of n. That will be important. These numbers are important to generate our next guess for m sub n plus 1. So you need to save these numbers and use them at the top to compute the next initial guess. And then loop 1 ends. Okay, so go back to the top. Okay, that's the computational engine. I give you some code. I have to grade your code, so I have to make sure you compute something that I expect so that I can grade it. So I give you a little bit of code. I think in this particular problem, I give you very little. You're more or less on your own. But you can do it. So you just sat through 3 lectures on how to compute the Feigenbaum delta. It's the first really serious computation that you're going to be doing in this course. So I hope you spend the time and you work on it and you have great success. I'm Jeff Chasnov. Thanks for watching, and I'll see you in the next video.